All right, guys, this is the test review for the sequences and series test. On the left, we have an explicit sequence, and on the right, we have a recursive sequence. And for both of those, we are asked to find the first 5 terms. Just a reminder that a sequence is a list of numbers, and that a series, which we'll be dealing with later in the review, is the sum of a sequence. It's the sum of the numbers that you find. But for now, we are just finding a set of 5 numbers. They've asked us to find the first 5 terms. Now, this sequence on the left is explicit, and it's explicit because we don't need the previous term to find the next term. So I could say, find me a sub 500, the 500th term, and we would just plug 500 in. Negative 2 times 500 minus 7, and that's negative 1007. That's not part of our review. Don't do that right now. But we can just plug in that 500, and without having to know any of the other terms, we can find the 500th term. All right, let's find the first 5 terms. So term 1, a sub 1, is going to be negative 2 times 1 minus 7, which is negative 9. A sub 2 is negative 2 times 2 minus 7, which is negative 11. A sub 3 is negative 2 times 3 minus 7, and that's negative 13. If you are seeing a pattern, that is fabulous. A sub 4 is negative 2 times 4 minus 7, which is negative 15. And a sub 5 is negative 2 times 5 minus 7, which is negative 17. And so the first 5 terms of this sequence, and we do actually want to go ahead and write them out in a list, are negative 9, comma negative 11, negative 13, negative 15, and negative 17. And that's going to be our answer right there. All right, number 2 is a recursive sequence. And it's recursive because it looks back. And so in order to find the second term, I need the first term. And in order to find the third term, I need the first and the second. And for that reason, recursive sequences are sometimes less useful, because if I want the 500th term of a recursive sequence, I need term 499. And to have found term 499, I needed term 498. So we need all of the previous terms to find the next one. But in this case, we're doing good because they gave us the first term. We're going to go ahead and list that. A sub 1 is negative 5. And then a sub 2, my second term, is going to be 3 times a sub 2 minus 1 plus 4. And that is 3 times a sub 1 plus 4. And we know a sub 1, right? So that's 3 times negative 5 plus 4. And when you do that calculation, it's negative 11. And so notice that that negative 5 featured into the calculation of this second term. And when I go to find the third term, we're going to use the second term. So it's 3 times a sub 3 minus 1 plus 4, which is 3 times a sub 2 plus 4. And so that third term is 3 times negative 11 plus 4, which is negative 29. And again, note that that negative 11, that second term, featured in the calculation of this term right here. All right, a sub 4 is 3 times the previous term. In this case, it's negative 29 plus 4. And when you do that calculation, you get negative 83. And a sub 5 is 3 times the previous term, so that's negative 83 plus 4, which is negative 245. And so the first 5 terms of this sequence, and they asked for the first 5 terms, so even though they gave us term 1, we need to go ahead and write it out. So it's negative 5, comma, negative 11, negative 29, negative 83, and negative 245. All right, guys, for 3 and 4, we are writing an explicit formula for number 3 and a recursive formula for number 4. Explicit means that my formula will only have an n in it. I'm only needing the term number. I find that it is easiest to write these formulas when we make a table of the values so that we can more easily see their relationship. So for number 3, I have my n and my a sub n. So my term number and then the actual term. So my first term is 5, my second term is 8, my third term is 11, fourth is 14, and fifth is 17. And if you look at this, every time we move from one term to the next, we're adding 3. So plus 3, plus 3, plus 3. And that's actually what we're doing here is we're writing a linear equation that has a slope of 3. So a sub n is equal to 3n, because that's my slope. And then we have to ask ourselves, all right, well, if 3 is my slope, and my first point is 5, what's my y-intercept? So I know that I have a point at 1, 5, and that to get to that point, I went up 3 and right 1. And so where'd I start? Down 3, right? And so I started at the point 0, 2. And so my y-intercept here is 2. This is our explicit formula, 3n plus 2. And again, now I can find explicit means we don't need the previous term, so I could find the 500th or 1,000th term of this sequence without having to do, 499 or 999 calculations before I got there. All right, number 4 wants us to write a recursive formula, and sometimes these formulas are actually easier to write because we get to start our formula by saying, hey, I'm going to give you the first term. And so in this case, my first term is 3, and we give that to them, and that is part of our formula. And then we need to write the rest of the formula. So again, it is sometimes useful to make a table. So my first term is 3, and my second is 21, and my third is 147, and my fourth is 1,029. And so what we see when we look at this from term to term, what is happening is we're multiplying by 7. And if I were trying to write an explicit formula, I'd have to come up with some other relationship that relates the 3 there, but I don't have to because this is a recursive formula. So I get to give my, my students or my mathematicians, whoever is going to use the formula, I get to give them that first term. And so all I have to do is I have to say, hey, if you want the next term, multiply the previous term, a sub n minus 1 times 3. And so our formula actually looks like a sub 1 is 3, and a sub n is 3 times a sub n minus 1. And that's our formula. And both of those things are part of the formula, again, because we have to give that first term. So for number 5, they've asked us to expand and evaluate the following series. And so this notation you see for number 5 is called summation notation. That is a sigma right there, and that means add everything up. For this particular problem, they've asked us to start at 2 and stop at 6. And so we're going to add terms 2 to 6 of the series. All right, and so we need to know what those terms are in order to add them together. So what we do is we calculate those terms. So a sub 2 is 2 squared plus 1, which is 4 plus 1, and that's 5. A sub 3 is 3 squared plus 1, which is 9 plus 1, and that's 10. A sub 4 is 4 squared plus 1, that's 16 plus 1, and that's 17. a sub 5 is 5 squared plus 1, which is 25 plus 1, and that's 26. And a sub 6, which is the last term we need to calculate because that's a 6 that's on top of that sigma notation, is 6 squared plus 1, which is 36 plus 1, and that's 37. And so if we were dealing with a sequence, our answer would be 5, 10, 17, 26, 37. But since we are dealing with a series, we have to find the sum of those numbers. So the sum from n equals 2 to 6, so the second to sixth term of this series of n squared plus 1 is equal to 5 plus 10 plus 17 plus 26 plus 37. And we add those numbers all up. And when we do, we get 95. So that is our answer to this problem. The sum of terms 2 to 6 of this series is 95. For number 6, they want us to find the arithmetic sum of the given series. And they want us to use those formulas that we were given that we can use as sort of shortcuts to find the summation. And the reason we have these formulas is that while we were able to find the sum for question number 5 fairly easily, we were only looking at the sum of terms 2 through 6. And if you look at number 6, we're looking for the sum at 30. So we're looking for the sum of the first 30 terms of this problem. And so we don't want to sit and calculate 30 sums and then add those 30 numbers all together. So we want a shortcut for that. So I can use this awesome arithmetic sum formula as a shortcut. I need to know n, which is the term number, and in this case, that's 30. I need to know the first term, a sub 1, and I can find that fairly easily using my formula there. It's 2 times 1 plus 3, which is 5. And I need to know my term at the last position, so a sub n, so my last term that I'm calculating the sum for. And in this case, that's 30, so it's 2 times 30 plus 3, which for us is 63. And all we have to do is take these 3 numbers that we found and plug them into the sum formula. So for us, the sum at 30 is equal to 30 times a sub 1, which is 5, plus a sub 30, which is 63. This is the first term and the 30th term, all divided by 2. And when you do that calculation, you get 1,020. And so that is the sum of the first 30 terms of that series is 1,020. All right, guys, for number 7, we are going to use the sum formulas to find the sum of this geometric series. Just before we get started, guys, if you're looking at your review, you have a 1 in front of the 1/3 right here. That is a typo. That's a typo. It is not supposed to be there. Your series should look like the series that's right here on the screen. So it should start with a 1/3. It should not have a 1 in the front, and I apologize for that. All right, so if we are going to use the formula to find this geometric sum, again, this is a shortcut. I am finding the sum of the first 17 terms. That's 17 right there that's floating as a subscript on the S. What we do is we use our geometric sum formula, which requires that we know our first term, which we do, it's 1/3, our common ratio, which is R, and then N, the term we're going to. And we can find all of those things. So let's go ahead and just list our first term, a sub 1. That's 1/3. We've got that. That's the first number in our list. And N, we know, because it's right there as a subscript, we're going to term 17. And so that leaves us with our common ratio. And so the question is, what is our common ratio? And so if you look at how we get from 1/3 to 2/3, 2/3 to 4/3, 4/3 to 8/3, and 8/3 to 16/3, what you notice is that the number on top of the fraction is being multiplied by 2 each time. And so that's our ratio right there. R is equal to 2. Don't worry that it's on top of a third. All right, and so we just plug these numbers into our formula. So our sum at 17 is equal to 1/3, 1 minus 2 to the 17th power, divided by 1 minus 2. And when you do that sum calculation, when you calculate that number, you get 43,690.3 repeating. So, and 1/3. And that is the sum of the first 17 terms in this series here. And the reason that that sum is so much bigger than the other one is that instead of just adding a couple numbers each time, we are multiplying each of these numbers by 2 every time. And so when you get up to 17, you've got a pretty large number. But that's our sum right there, 43,690.3 repeating. And finally, number 8, where we are going to take a given series, a given sum, and we are going to use sigma notation to write a formula to write this sum so that you could box this sum up and take it someplace else and write it out for someone else, or hand somebody else this formula and they could produce the same sum. So the way we want to do this is we want to figure out what is the formula that goes into this. And again, I've told you before, guys, that I really recommend that you make a table of values. And so we're going to do that, n and a sub n. So our table of values. So my first term is 1/2. My second term is 2. My third term is 9/2. Fourth term is 8. And fifth is 25/2. And if you think that you're seeing sort of a pattern, you probably are. If you notice 9/2, this third term right here, 9/2, we could write that as 3 squared over 2. And this fifth term right here, 25/2, we could write that as 5 squared over 2. And if you look at this, you're looking at the second term right here of 2. We ask ourselves, well, is that 2 squared divided by 2? And 2 squared is 4, and 4 divided by 2 is 2. And then we can ask the same thing about the fourth term, is 8 4 squared divided by 2? And 4 squared is 16, divided by 2 is 8. And so we've got a pattern here where our a sub n, our term, is equal to n squared divided by 2. And it goes almost without saying, but that applies to the first term as well, right? 1 squared divided by 2 is just 1/2. So that's our formula. Way to go, us. And then we look at this and we say, okay, we've got to fill in the rest of the summation notation. So we draw our sigma, and then the series we're dealing with always start at 1. We're going to start at 1. And then you ask, well, where does this end? It starts at 1, but where does it end? And if you look, you see these ... dots right here. And that ... means we're going to infinity. So on top, we put an infinity because that series is not going to stop anytime soon. You're starting at n equals 1, we're going to infinity, and then next to the sigma notation is the formula we're going to use, which for us, our formula is n squared divided by 2. And that is the answer to this problem right there. But we did have to find those values first. We did have to write out our table and figure out the formula before we could put it in sigma notation. All right, guys, test tomorrow. You're going to have the formulas and you're going to have a calculator. You just need to make sure that you can, evaluate formulas and that you know how to use the arithmetic and geometric summation formulas that we used in this review.